2.5 million light-years away, an island of 1 trillion stars is drifting toward us at 110 kilometers every second. Its light, leaving when our ancestors first chipped stone, is only now reaching your eyes. Andromeda is the largest thing the unaided human eye can see, and almost everything you have been told about its arrival is being quietly rewritten. Tonight, we will travel outward from a single human breath into the pale smudge above the autumn horizon, crossing the empty rooms between galaxies, descending into a foreign disk and a foreign black hole, and discovering why the most famous prediction in modern astronomy may no longer be true. Before we dive in, if you love exploring the deep cosmos as much as we do, take a second to like the video or subscribe, and tell me where you're listening from and what time it is. Now let's begin. To understand what we are about to do, you need to first understand where you are. Not the city, not the country, not even the planet. Begin a layer below all of that. Begin with the small fact that you are sitting or lying somewhere on the surface of a rocky world that orbits an average yellow star, and that this star is one of 200 to 400 billion stars bound together in a slowly turning pinwheel of gas and dust and dark matter that we call the Milky Way. The Milky Way is enormous by any human measure. It would take light, the fastest thing in the universe, roughly 100,000 years to cross from one edge of its disk to the other. And yet, as galaxies go, ours is unremarkable. It is one ordinary spiral among uncounted others, drifting in a thinly populated corner of a much larger structure called the local group. Now look up. If the night above you is dark enough, far from city lights on a clear autumn evening, somewhere away from the haze of street lamps, and if you know exactly where to aim your eye, you can find a faint patch of pale light high in the constellation Andromeda. It looks nothing like a star. It does not twinkle. It has no edges. It seems almost like a smudge of breath on cold glass, a bruise of milky gray against the black. Most people who have looked up at the night sky their entire lives have never seen it, because their eyes did not know what to look for. But it is there, unfailingly, every clear autumn night, hanging above the northern horizon like a piece of fog that refuses to dissolve. That smudge is not gas. It is not a cloud. It is not part of our galaxy. It is another galaxy, larger than our own, with more stars than our own. And the photons reaching your eyes left it 2.5 million years ago, when our ancestors were first learning to chip flakes from stone. The light is older than language. The light is older than fire. The light is older than the species that is now using it to look back. Hold this thought as we begin. Every photon from Andromeda that lands on your retina has been traveling in a perfectly straight line for longer than humans have existed. It crossed the cold dark between two galaxies for 100,000 human generations, never bending, never slowing, until at last it intersected the lens of your eye on this particular evening, on this particular planet, in this particular century. Most of those photons land instead on rock, on dust, on empty asphalt, on closed eyelids. The few that find a watching eye carry with them a piece of a place no human has ever come close to visiting. To look at Andromeda is to receive a letter from a distant city that no longer exists in the form the letter describes, because the city has gone on living for 2.5 million years since the letter was sent. Take a moment with that. There is no shortcut around the slowness of light. There is no faster channel. The smudge above the autumn sky is the freshest possible image we can have of this place, and it is already 2.5 million years out of date. Andromeda has many names. The catalogues call it M31, the 31st object in the 18th century list compiled by the French comet hunter Charles Messier. Astronomers also call it NGC 224 after the New General Catalogue. But the oldest known written record of it is far more poetic. In the year 964, an Islamic astronomer named Abd al-Rahman al-Sufi, working in the great library culture of medieval Persia, completed a beautiful book called the Book of Fixed Stars. In it, he described with care and exactness a faint cloud in the constellation he called the Chained Lady. He had no idea what it was. He could not have. But he wrote it down, and the description survived. And 1,000 years later, we know that he was the first human being on record to take note of an entire other galaxy. He thought he was looking at a small smear of mist among the stars. He was looking at 1 trillion suns. For most of the centuries that followed al-Sufi, almost nothing changed in our understanding of the smudge. Telescopes improved. Astronomers gave it a number, gave it a constellation, and gave it a position in the sky. But everyone, even the great observers of the 17th and 18th centuries, assumed that this fuzzy patch of light was a small object inside our own Milky Way. A nebula, a swirl of glowing gas, a nearby cloud, perhaps a few thousand light years out, somewhere among the stars we already knew. The idea that it might be a separate galaxy, an entire other Milky Way drifting alone in deeper space, would have struck most astronomers before the 20th century as something close to nonsense. The Milky Way, in the consensus picture of that time, was the universe. There was nothing outside it. The smudge in Andromeda had to be inside it, somewhere, somehow. The story of how that picture broke is one of the great quiet revolutions in human thought, and it ran through a single mountaintop in Southern California. At the Mount Wilson Observatory, perched above the smog of Los Angeles in the San Gabriel Mountains, a young astronomer named Edwin Hubble was patiently photographing the Andromeda smudge night after night with the new 100-inch Hooker telescope, the largest in the world. He was looking for a particular kind of star. Cepheid variables, pulsing stars whose brightness rises and falls on a clockwork schedule, and whose intrinsic brightness can be calculated from the rhythm of their pulsing. If you know how bright a star truly is, and you know how bright it appears from Earth, you can calculate exactly how far away it must be. Cepheids are, in this sense, cosmic lighthouses. Their flashes carry distance information. In 1924, Hubble found one, then another, then more. He measured their pulses. He calculated their true brightness. He compared that to how dim they appeared on his photographic plates. And the answer he got back was that the Andromeda smudge was not a few thousand light years away. It was nearly 1 million light years, vastly outside the Milky Way. Later, after Walter Bader's 1953 work on Cepheid populations, the distance would be revised upward, eventually settling near today's value of 2.5 million light-years. It was vastly outside the Milky Way. It was its own galaxy. The universe, in a single instant, became almost incomprehensibly larger than anyone had imagined. The smudge had stars. The smudge had a center. The smudge had a structure. The smudge was, in every essential way, another version of the place we already lived in. Stay with this for a moment. There is something profoundly strange about the kind of discovery Hubble made. He did not invent anything. He did not build anything. He simply looked carefully enough, for long enough, at a piece of the sky that had been visible to every human being who had ever lived. The truth had been pouring down on the surface of the Earth in the form of photons for the entire history of our species. It had landed on the eyes of pharaohs, on the eyes of farmers, on the eyes of monks and merchants and children. None of them had instruments capable of decoding it. The information was there. The information had always been there. We simply had not yet built the machinery to read it. That is one of the lessons Andromeda keeps teaching us. Many of the most important truths about the universe are not hidden in the sense of being far away or behind a wall. They are hidden in the sense that they require new ways of measuring, new ways of comparing, new ways of paying attention. Andromeda did not become a galaxy in 1924. It had always been a galaxy. We simply, in 1924, became capable of seeing what it was. Now we turn to a different question, one that will hover over everything we say tonight. How big, exactly, is this thing you are looking at? The answer is that we are not entirely sure, and the uncertainty is not small. Recent measurements, averaged across many independent methods, place Andromeda at roughly 2.5 million light-years from Earth, somewhere around 2.5 to 2.54 million light-years, with an honest scientific error bar of plus or minus about 100,000 light-years. That uncertainty alone, the wiggle room in our distance estimate, is roughly the diameter of our entire Milky Way. Across 2.5 million light-years, our best telescopes still cannot pin Andromeda's location to better than about a Milky Way's width. That is not a failing of the astronomers. That is the cost of measuring distances on a cosmic scale. The galaxy itself, by current estimates, is around 200,000 light-years across at its widest, although different definitions of where the disk ends produce different numbers. It contains, depending on which dataset you use and which corrections you apply, somewhere on the order of 1 trillion stars, roughly 2 to 3 times the population of our own Milky Way. Its total mass is something on the order of 1 to 1.5 trillion times the mass of our Sun. That includes the vast invisible halo of dark matter that surrounds it like a ghostly cocoon. Recent work suggests the number may be closer to the lower end of that range. Some researchers put it heavier than the Milky Way. Others put it roughly equal. The honest answer is that the 2 largest galaxies in our local cosmic neighborhood may be near twins in mass, or Andromeda may be the bigger of the 2. We do not yet know with the kind of certainty we would like. Stay with this strangeness for a moment. The closest large galaxy to ours, the one we have been studying for 1,000 years, the one whose photograph hangs in every astronomy textbook, is something whose mass we cannot pin down to better than about a factor of 2. Imagine being unable to tell whether your closest neighbor weighed 80 kilograms or 160. Now imagine that this neighbor lives just across the street and you have nothing better to do than measure them. That is roughly our position with respect to Andromeda. It is the easiest large galaxy to measure in the universe, and it is still, in many ways, a mystery. There is something else worth saying before we leave the surface of the Earth and begin our journey outward. Andromeda is not standing still. It is moving, and it is moving toward us. In 1912, the American astronomer Vesto Slipher, working at the Lowell Observatory in Flagstaff, Arizona, the same observatory where Pluto would later be discovered, pointed a spectrograph at the Andromeda smudge and split its light into a rainbow. He measured the dark lines in that rainbow, the absorption lines that mark where elements in the atmospheres of stars eat specific wavelengths. And he noticed something extraordinary. The lines were shifted, not redward, toward longer wavelengths, as they would be for an object moving away. They were shifted blueward toward shorter wavelengths, as they would be for an object moving toward the observer. Slipher concluded, correctly, that the Andromeda smudge was approaching the Sun at roughly 300 kilometers per second. That was 1912. The number has been refined since. The current best estimate of Andromeda's radial velocity, the speed at which it is moving directly toward us, is about 110 kilometers per second. The change in the number does not mean Andromeda has slowed down. It means our position in the Milky Way has its own motion that has to be accounted for. When you correct for the Sun's orbital movement around the galactic center, the relative approach speed of the Andromeda galaxy to our own galaxy comes out to that 110 kilometers per second figure. Every second, we and our nearest large neighbor are 110 kilometers closer than we were the second before. Every minute, 6,600 kilometers closer. Every hour, 400,000 kilometers closer. You will want to think this is fast. By any human measure, it is. 110 kilometers per second is well over 1,000 times the speed of a passenger jet. Nothing on Earth, not a missile, not a rocket, not a railgun slug, moves at that speed. And yet, against the unimaginable distance between us and Andromeda, this speed is glacial. At 110 kilometers per second, sustained without slowing, it would still take Andromeda many billions of years to reach the Milky Way. That is one of the first quiet truths the universe asks you to absorb on a journey like this one. The numbers that govern motion on a cosmic scale are simultaneously enormous and meaningless. A galaxy can be screaming toward you at 110 kilometers per second and still take longer to arrive than the entire history of life on Earth. The physics is fast, the geometry is slow, and in the gap between those two facts, we live our entire civilization and never once feel the wind of the approaching galaxy on our faces. So this is the picture so far. You are sitting on a rocky planet around an ordinary star inside one ordinary spiral galaxy. Above you, in the autumn sky, hangs the faint smudge of another spiral galaxy, larger than ours, holding 1 trillion stars and a black hole 100 million times the mass of our own sun. That galaxy is 2.5 million light-years away, give or take, and it is moving toward us at 110 kilometers per second. Its light, when you see it, is older than your species. Its mass, when measured, is uncertain by nearly a factor of 2. Its fate, when simulated, is no longer the single tidy answer it once seemed to be. And the question of whether it will ever actually meet our galaxy in some final cosmic embrace is now, for the first time in a generation, a coin flip rather than a certainty. This is the picture, and it has a 1,000-year history of being told confidently. The smudge is Andromeda. Andromeda is huge. Andromeda is rushing toward us. Andromeda will collide with the Milky Way somewhere around 4 to 5 billion years from now, and the night sky and the deep future of our planet will be swallowed by an arrival of fire. That is the picture you have most likely been told. That picture is, as of June 2025, no longer the consensus. A team of astronomers led by Till Sawala at the University of Helsinki in Finland, working alongside colleagues at Durham University in the United Kingdom, the University of Toulouse in France, and the University of Western Australia, published a careful new analysis in the journal Nature Astronomy, using observational data from both the Hubble Space Telescope and the European Space Agency's Gaia spacecraft. They considered more than 20 different variables with non-negligible uncertainties. They ran tens of thousands of Monte Carlo simulations of the local group's evolution over the next 10 billion years. What they found was not a confirmation of the old story. What they found was a coin flip. There is, by their best estimate, roughly a 50% probability that the Milky Way and Andromeda merge within the next 10 billion years. The other 50% of the time, in their simulations, the two galaxies pass each other in the dark, miss, drift apart, or take so long to fall back together that they barely interact across the lifespan of the universe as we currently understand it. The picture has not been overturned. It has been quietly, beautifully made uncertain again. This is one of the threads we will follow tonight. Hold on to it. The question of what happens when Andromeda arrives, or whether it arrives at all, is the largest of the loops we will leave open as we travel. We will not answer it until the very end. By the time we do, your understanding of what a galactic encounter means will not be the same. There are smaller threads to keep in mind too. There is the strange double nucleus at the heart of Andromeda, two bright knots of stars that share a single galactic core, separated by only 5 light years, with a supermassive black hole hidden inside one of them. We will arrive there before the night ends, but the answer to why it is double is not yet fully settled, and it has to do with a violent event in Andromeda's past. There is the strange small companion galaxy called M32, sitting close beside Andromeda like a wounded child, a small dense ball of stars whose origin, until recently, was a complete mystery. We will discover what it actually was, and what it did, and how its scars are still visible across Andromeda's face. There is the long, ghostly arc of stars stretching out of Andromeda's southern flank, called the Giant Stream, a feature first noticed only in 2001, which tells us a story about a galaxy that Andromeda ate so long ago that no living thing on Earth was complex enough to witness the meal. We will see all of these, but for now, hold them as questions. Andromeda has secrets. Andromeda has wounds. Andromeda has a fate that is no longer settled. There is one more thing worth saying before we begin to move. You are about to take a journey across 2.5 million light years. No physical object can do this. No physical object will ever do this, not in any realistic technological future. Voyager 1, our farthest probe, traveling at roughly 17 kilometers per second, has been moving outward for almost half a century. It has not yet left the gravitational influence of the Sun. At its current speed, Voyager 1 would take more than 40 billion years to reach Andromeda. That is roughly 3 times the current age of the universe. The galaxy you are about to visit is, in any practical sense, unreachable. The trip you are about to take is not a trip your body can ever make, but the imagination can move at any speed it wants. The imagination has no fuel limit. The imagination can stand at the threshold of a planet, fall outward through the solar system, cross the spiral of the Milky Way, drift across the void of intergalactic space, and approach the edge of another disk in the time it takes you to listen to a story. So that is what we are going to do. The picture so far is this: Earth beneath you, sky above you. 2.5 million light years away, a smudge that is not a smudge. A galaxy of 1 trillion stars, weighing 1 trillion suns, drifting toward us at 110 kilometers per second, whose fate when it meets us is no longer certain. Hold the smudge in your mind. Now begin to lift away from the surface. Imagine yourself rising, slowly, from the place you are listening. Not as a body, but as a point of attention. The room around you grows small. The roof of the building thins to a line, then disappears. You can see the lights of your city below, a yellow grid stretched across dark land. You rise faster. Cities become clusters. Clusters become coastlines. Coastlines become continents. The horizon curves. The atmosphere thins to a smear of blue. And then, almost gently, the blue is gone, and you are floating in the cold black above the daylight side of the Earth, watching the planet turn beneath you as a cloud-marbled sphere. From here, the smudge of Andromeda is still where it was, still 2.5 million light-years away, still drifting toward us. The view has not changed. Distance on this scale is unmoved by the act of leaving the planet. Keep going. The Earth shrinks behind you. The Moon swings past, a pale grey disk, its craters precise and shadowed, and falls into the same shrinking distance as the planet you came from. You pass the orbit of Mars, a rust-red ball with thin clouds and white poles. You pass the orbit of Jupiter, a banded giant whose great storm could swallow your entire home planet without straining. Saturn flickers by, its rings a thin blade of ice and dust catching the sun. Then the orbits begin to spread. Uranus, Neptune, the Kuiper Belt with its slow scattered ices, its Plutos and Eris's. And then, beyond all of these, you cross into a region that has no clear edge, the heliopause, where the wind of charged particles streaming off the sun finally meets the cold thin gas between the stars. Voyager 1 crossed this boundary in August 2012, after 35 years of flying. Voyager 2 followed 6 years later, in November 2018. Beyond it, you are no longer in the sun's neighborhood. You are in the wider interstellar medium. You have left the solar system. This is not the journey. This is only the first step of the journey. Stay with this for a moment, because the geometry that follows depends on your truly absorbing what just happened. The solar system, from edge to edge, even being generous and counting the distant Oort cloud, the spherical shell of icy bodies that may extend a light year or more from the sun, is, on a galactic scale, a single grain of sand. The distances we have just covered, distances that took Voyager half a human lifetime to traverse, are essentially nothing in the units we will be using from here onward. From the Sun to the next nearest star, Proxima Centauri, is a little over 4 light-years. From Proxima Centauri to the far side of the Milky Way is roughly 100,000 light-years. From the Milky Way to Andromeda is 2.5 million. We have not yet left the front step of the cosmic house. The continent is still ahead of us. The first thing you would notice, drifting outward from the solar system, is the silence. There is no air for sound to move through, but more than that, there is nothing close enough to make sound matter. The sun, behind you, has shrunk to a sharp white point, no larger than the brightest star in any sky you have ever seen. It is still the brightest thing in this part of space, but only barely. Other stars, similar in luminosity, are scattered around you in a sphere that no longer has a center. There is no up. There is no down. There is no horizon. There is only direction. And one of those directions, you slowly realize, is where you are headed. If you turn and look back, you can find the sun. It is recognizable only because you know exactly where to look. Beyond it, you can find Sirius, the brightest star in Earth's sky, though from here it is no longer the brightest. The constellations have started to deform. The patterns we drew lines between for thousands of years, Orion, the Big Dipper, Cassiopeia, are visible only in the small patch of sky where the sun still hangs. And even in that small patch, they are beginning to slide and shift. The sun, from your new perspective, is part of an obscure constellation in some other star's sky. The pattern of stars we have memorized for our entire civilization is a local accident. It is not the universe. It is a piece of furniture in a single room of a house we are only now stepping out of. A spine checkpoint then, before we go further. We have just left the solar system. We are roughly 1 to 2 light years from the Sun. The smudge of Andromeda is still where it was, 2.5 million light years away. We have not closed the distance in any meaningful way. Imagine a journey of 1 million steps. We have just taken one. Hold the smallness of this for a moment. It will become important. In front of you, scattered across the next leg of the journey, are the stars of our local stellar neighborhood. There are perhaps 1,000 stars within 50 light years of the Sun. Most of them are red dwarfs, small, cool, dim, with lifespans longer than the current age of the universe. A few are sun-like, a handful are giants, some have planets. A growing number since the early 2000s have planets that astronomers have actually detected and characterized. The first confirmed exoplanet around a sun-like star, 51 Pegasi b, was found in 1995 by the Swiss astronomers Michel Maillot and Didier Queloz, working from the Haute-Provence Observatory in southern France. They were given the Nobel Prize for it in 2019. Today, the count of confirmed exoplanets is in the thousands, and many of them lie along the corridor we are about to fly through. Around some of these stars there may be water. Around some, there may be atmospheres. Around some, in some sense we cannot yet measure, there may be life. Pause on that thought. The corridor between you and the heart of the Milky Way is not empty. It is full of worlds. We do not know how many of them are inhabited, or whether any of them are. But the fact that some of them might be is one of the quiet weights that hangs over a journey like this one. Andromeda lies on the far side of all of these places. To see Andromeda, the photons that reach your eyes had to pass through this neighborhood, past Proxima, past Sirius, past Vega, past every system whose star we have named, and arrive at our planet only after a final crossing of the dark. Onward. The stars around you begin to thicken. The Milky Way, viewed from the inside, is a flattened disk roughly 100,000 light-years across and a few thousand light-years thick, with a central bulge of older, redder stars and a series of spiral arms wrapping outward like the slow curls of a hurricane. Our Sun lives in one of the smaller arms, the Orion Arm, about 26,000 light-years from the galactic center. To reach the far edge of the disk, you have to cross most of the diameter of the galaxy, and in doing so, pass through layers of stars, dust clouds, and star-forming regions that look, from our position, like the band of light that gives the galaxy its name. From inside, that band is not a feature. It is the rest of the disk you are inside of, viewed edge-on. Begin to descend toward the plane of the Milky Way. The dust thickens. You enter the molecular clouds, vast cold regions of hydrogen and helium, and trace amounts of heavier elements where new stars are still being born. The Orion Nebula, which from Earth looks like a faint blur in the sword of the constellation Orion, becomes a glowing canyon of ionized gas, lit from within by hot young stars whose ultraviolet light tears through the surrounding cloud. The Carina Nebula in the southern sky becomes a wall of pillars and filaments stretched over hundreds of light years. The Eagle Nebula, with its famous pillars of creation, becomes a small forest of fingers reaching out of a curtain of gas, each finger holding the seeds of stars not yet born. These places from Earth are decorations. From up close, they are nurseries the size of solar systems. The dust gets in your way. The center of the Milky Way, when viewed at visible wavelengths from inside the disk, is hidden behind layers of dust that absorb almost all the light coming from it. To see toward the galactic core, you have to look at infrared or radio wavelengths, where the dust becomes transparent. In radio, the center is bright. There is a sharp, compact source of radio emission at the very heart of the Milky Way, a source named Sagittarius A star, pronounced Sagittarius A star, and it is a supermassive black hole. Its mass, measured precisely by tracking the orbits of stars near the galactic center over the course of decades, is approximately 4 million times the mass of the Sun. The astronomers Reinhard Genzel and Andrea Ghez, working independently, Genzel at the Max Planck Institute for Extraterrestrial Physics near Munich, Germany, using telescopes at the European Southern Observatory in Chile, and Ghez at UCLA in California, using the Keck Observatory in Hawaii, were awarded the Nobel Prize in 2020 for that measurement. They had watched stars whip around something invisible, and from the speed of those stars, they had weighed the invisible thing. That black hole sits at the center of our galaxy. It is, by galactic standards, modest. Andromeda's central black hole is roughly 25 to 50 times more massive than ours, somewhere between 100 and 200 million solar masses. We will arrive at it tonight. But first, we still have to cross the Milky Way to reach the side that faces Andromeda. Continue forward. The disk slides past you. The Sun, now behind you, has long since shrunk to nothing. The galactic center hangs to one side, a glowing pile of stars and dust, and the occasional shockwave from a passing supernova. The arms curl outward. You see the layered structure of the galaxy, the thin disk of young stars and gas, the thick disk of older stars, the spheroidal halo of ancient stars that reaches up out of the plane in every direction. You see the globular clusters, dense balls of hundreds of thousands of old stars, scattered like jeweled bees through the halo, each one tens of billions of years old. You see, in the distance, the large and small Magellanic Clouds, two satellite galaxies of the Milky Way, much smaller than our own galaxy, but still containing billions of stars each. The large Magellanic Cloud, in particular, will matter later. It is one of the variables in Sewala's simulation. The presence of its mass, hanging off the edge of the Milky Way, can tug our galaxy off the orbital plane that would otherwise lead to a head-on collision with Andromeda. It is, in a strange sense, a small companion that may be quietly steering us out of harm's way. But that is a thread for later, a spine checkpoint. We are now near the far edge of the Milky Way's disk, perhaps 80,000 light-years from where we started. The Sun is gone. The galactic core is shrinking behind us. Ahead is the halo, a sphere of old stars and dark matter that surrounds the entire disk. Beyond the halo is the cold dark between galaxies. We have not yet really begun to close on Andromeda. We have only begun to leave home. The halo of the Milky Way is a strange place. Most of its stars are old, formed in the first few billion years of the galaxy's existence, when matter was still organizing itself into the structures we see today. The halo's stars are spread out, moving on long looping orbits that take them millions of years to complete. They are metal poor in astronomical terms, meaning they have very little of any element heavier than hydrogen and helium, because those heavier elements had not yet been forged in the cores of earlier stars. To walk through the halo is to walk among the oldest things our galaxy has. Some of its globular clusters formed in the first 500 million years after the Big Bang. They are older than every rock on Earth. They are older than every fossil. They are older than every species. They are very nearly as old as the universe itself. But the halo is not full. It is sparse. The density of stars in the halo is so low that you could fly through it in a straight line for thousands of light years and never come within a single light year of any star. The halo is a sphere of widely scattered ancient witnesses. Most of it is empty, and beyond the halo, the emptiness deepens. You begin to cross out of the gravitational reach of the Milky Way's stars and into the region where dark matter still dominates, but the visible mass has thinned almost to nothing. You are now in the territory the Milky Way calls its own outermost edge, and Andromeda, far ahead, has its own outermost edge approaching from the other side. Between you and it is a place that has no stars at all. Stay with this strangeness. There is a region between galaxies that has no stars. Not a few stars, not sparse stars, no stars. It is not a hard boundary, but as a practical matter, the volume of space between the Milky Way's outer halo and Andromeda's outer halo is one of the emptiest places in the universe accessible to us. Single hydrogen atoms drift through it, more thinly spread than anything you can imagine. A cubic meter of intergalactic space contains, on average, a handful of atoms. A cubic meter of the air around you contains around 25 quintillion atoms. The void you are about to cross is, in an absolutely literal sense, the closest thing the universe has to nothing. A spine checkpoint, the last for this leg. We are now at the gravitational edge of the Milky Way, perhaps 1 to 200,000 light-years from where we started. Behind us, our galaxy hangs like a glowing wheel. Bright core, dark dust lanes, sparkling spiral arms, a pale halo of old stars stretched in every direction. Ahead, the Andromeda smudge is still where it was, still 2.5 million light-years away from where we started. But from here, with no Earth atmosphere distorting your view and no sun's glare washing out the dim, the smudge is no longer a smudge. It is a galaxy. You can begin to see its structure. You can see the brighter knot of its core, the twisted pattern of its arms, the dim halo of stars and gas that surrounds it. You can see, with a kind of uncomfortable directness, that the thing you are looking at is shaped like the thing behind you. The next leg of the journey is the longest. 2.5 million light-years of nearly empty space. No stars, almost no atoms, almost no light, except the photons leaving the galaxy behind you and the photons leaving the galaxy ahead of you, both passing through the dark and arriving, eventually, somewhere. Take a slow breath. The void waits. The void between galaxies is the strangest country you will ever pass through. Imagine, if you can, a place where in every direction you look, there is nothing close. Not a star within tens of thousands of light years. Not a planet within hundreds of millions of years of any direction. The space around you is not even truly empty in the absolute sense. There are stray photons, a faint hum of microwave radiation left over from the early universe, the occasional drifting hydrogen atom, the occasional cold dust grain. But for any practical purpose, you are passing through the cleanest, deepest, quietest, oldest emptiness anywhere in the cosmos. The vacuum of intergalactic space is purer than the vacuum of any laboratory ever built on Earth. The cosmic microwave background hums around you in every direction. It is the cooled-down afterglow of the Big Bang, redshifted now to a temperature of roughly 2.7 Kelvin. About 270 degrees below zero on the Celsius scale, only a few degrees above absolute zero. If you had instruments sensitive enough, you could measure tiny fluctuations in this glow, fluctuations on the order of 1 part in 100,000, which encode the seed pattern from which every galaxy, every star, every planet, and every living thing in the universe ultimately grew. The radio astronomers Arno Penzias and Robert Wilson, working at Bell Laboratories in Holmdel, New Jersey, accidentally discovered this background hum in 1964, while trying to figure out why their radio antenna kept picking up an unexplained hiss. The hiss turned out to be the universe's first photons, still in flight, still arriving. They received the Nobel Prize in 1978 for that accident. As you drift through the void between the Milky Way and Andromeda, those same photons are landing on you now. The same photons that landed on Penzias and Wilson. The same photons that will go on landing on every observer everywhere until the universe finally fades. That is the texture of the place you are crossing. It is mostly nothing, but nothing is whispering. Look around. Behind you, the Milky Way is a flat coin of light, perhaps a hand's breadth across at the distance you have now reached. Ahead, the Andromeda smudge is growing. It is no longer a stamp. It is no longer a coin. It is becoming a window, an oval window of soft glow hanging in the dark with structure visible inside it. To one side, you can see the small spiral of M33, also called the Triangulum Galaxy, the third largest member of the local group. M33 is bound to Andromeda gravitationally, orbiting it on a long elliptical path. In the Sawala simulations of 2025, M33's mass, roughly 50 billion solar masses, slightly increases the probability that Andromeda and the Milky Way merge. Its extra weight pulls our galaxy a little harder toward Andromeda. But it is one of many factors, and not, by itself, decisive. There are smaller galaxies too, dozens of them. Dwarf galaxies, small clumps of stars and dark matter, orbiting both the Milky Way and Andromeda, like a swarm of moths around two main lamps. The large and small Magellanic Clouds belong to our galaxy. The Triangulum Galaxy belongs to Andromeda. There are also IC10, NGC 147, NGC 185, and a long list of even smaller dwarfs whose names rarely make it into popular textbooks. Together, this loose family of galaxies makes up the local group, a structure perhaps 10 million light-years across, gravitationally bound, slowly turning, slowly evolving, and over the next few billion years, possibly destined to become a single object, or possibly not. The future of the local group, as Till Sawala's team put it in their 2025 paper, is genuinely uncertain. Some of these galaxies will fall into the Milky Way and Andromeda over time. Some will be flung out. Some will continue their patient, looping orbits. The system, as a whole, has not yet stabilized. Stay with that for a moment. The local group is still being made. The neighborhood you live in is not finished. It is in the middle of a slow gravitational drama whose final shape is still being negotiated. The galaxies you see around you, drifting in the dark, are characters in a story whose ending has not yet been written. You happen to live in the era when the principal characters are still arguing about where to stand. The void between galaxies is so quiet that you might begin, at this point in the journey, to feel a kind of small alarm. The numbers stop being meaningful. 2.5 million light-years is, in some honest sense, beyond what your nervous system can hold. Light, the fastest thing the universe permits, takes 2.5 million years to traverse this distance. 1 million human civilizations, each lasting 1,000 years, would rise and fall in the time required for a single photon to travel from the place you came from to the place you are going. And yet, on the cosmic scale, this distance is small. The Andromeda Galaxy is, within the local cosmos, our neighbor. The next galaxy of comparable size beyond Andromeda is the M81 group, around 12 million light-years away. Beyond that lies the Virgo cluster, 60 million light-years out, with thousands of galaxies bound together. Beyond that is the Laniakea supercluster, on the order of 500 million light-years across, of which our entire local group is a small dim outskirt. We are not the center of anything. We are a small island family in an ocean whose far shores we will never reach. But you are reaching one of them. The Andromeda smudge ahead of you is no longer a smudge. It is now a galaxy, large and bright. Its outer halo is becoming visible, not as a sharp edge, but as a slowly fading fog of stars and dark matter that extends in every direction outward from the bright disk in the middle. As you approach, you cross into that halo. You have, in some technical sense, arrived. A spine checkpoint. We are now inside the gravitational reach of the Andromeda galaxy. Roughly 2 million light-years separate us from the galaxy we left behind. Roughly 500,000 light-years separate us from the bright disk ahead. We have crossed the largest part of the void. The hardest, longest, emptiest part of the journey is behind us. From here on, you will have stars again. The outer halo of Andromeda is, like the outer halo of the Milky Way, sparse and old. It is populated by ancient stars, globular clusters, and the long debris streams of smaller galaxies that Andromeda has shredded and absorbed over its long history. The most famous of these debris streams is the one we mentioned earlier, the Giant Stream, first noticed in 2001 by an international team of astronomers, prominently including Rodrigo Ibata of the Strasbourg Observatory in France and Annette Ferguson, then working in the Netherlands. They were carrying out a deep survey of Andromeda's outskirts using a wide-field camera on the Isaac Newton telescope at the Roque de los Muchachos Observatory on the island of La Palma in the Canary Islands. They found, stretching out from the southern flank of Andromeda for hundreds of thousands of light-years, a long curved arc of stars that did not belong to any known structure. It looked like a wake. It looked like the trail of something that had passed through. That is exactly what it was. The Giant Stream is the smeared remains of a small galaxy that fell into Andromeda, was torn apart by tidal forces, and is now stretched into a long arc as it slowly rains down onto the larger galaxy. The stars in the stream still carry in their motions the memory of the parent galaxy that birthed them. By tracing the stream backward, astronomers can reconstruct the orbit of the swallowed galaxy. By measuring the star's chemical compositions, they can guess at the parent's age and mass. According to a 2018 paper by Richard D'Souza and Eric Bell of the University of Michigan in Ann Arbor, the most likely scenario is that this swallowed galaxy was once the third largest galaxy in the local group, larger even than M33, and that it spiraled into Andromeda roughly 2 billion years ago in a major collision that profoundly reshaped the larger galaxy. The shocking implication of D'Souza and Bell's work is that the small companion galaxy, M32, the dense little ball of stars that sits beside Andromeda today, is the leftover core of that swallowed giant. M32 is what is left of a galaxy Andromeda 8. The Giant Stream is the trail of the meal. That is the resolution of one of the threads we left earlier. The strange small companion, the wounded child beside its parent. M32 is not, in fact, a child. It is the surviving heart of an older, larger sibling. It is a fossil. The bright knot you see beside Andromeda when you look through a telescope is the unburied core of a galaxy that died here. Stay with this for a moment. Andromeda has a history of violence. Like our own galaxy, it has eaten smaller things. Unlike our own galaxy, the meal it had 2 billion years ago was huge, a true major merger, the kind of event that reorganizes the structure of a galaxy from the inside out. The thick disk of older stars that we see in Andromeda today, the metal-rich halo that surrounds it, the warped shape of its outer regions, the very pattern of star formation along its rings, all of it bears the fingerprint of that swallowed giant. Andromeda is not a quiet sister to the Milky Way. Andromeda has been through more. The signs of past trauma are written in the orbits of its stars and the chemistry of its halo. Move closer. The halo thins around you and the stars begin to thicken. You can now see Andromeda's globular clusters more clearly. Small, dense balls of ancient stars, each holding tens to hundreds of thousands of suns, scattered across the halo like quiet observers. There are around 500 globular clusters known to be associated with Andromeda, roughly 3 times the number associated with the Milky Way. Each of them is a city of old stars. Each of them is a relic from a time when Andromeda was younger and hungrier, gathering its mass from smaller building blocks. Some of them, astronomers suspect, were not originally part of Andromeda at all. They were the cores of dwarf galaxies that fell in long ago, were stripped of their loose stars and gas, and left behind only their tightest, densest cores, which now drift through Andromeda's halo as silent witnesses. You begin to see the bright disk now without ambiguity. It is enormous. It fills your field of view in a way that nothing has yet filled it. The whole experience of looking at the night sky from Earth has trained you to think of galaxies as small, distant, marginal, pinpoints in a black field. From here, just a few 100,000 light-years out, Andromeda is the field. It is a structured ocean of stars, with a glowing yellow core, a series of bluer outer arms threaded with bright pink star-forming regions, and a dark, interrupted lane of dust that traces the edge of the disk. Pause here. The disk is roughly 200,000 light-years across. It is twice the diameter of the Milky Way. It is one of the largest spiral galaxies in our cosmic neighborhood. And it is the place you are about to descend into, a spine checkpoint. We are now perhaps 100,000 light-years above Andromeda's disk, looking down on it from a steep angle. The disk is rotated roughly 77 degrees away from face-on, as seen from Earth, meaning that from our home, we see Andromeda nearly edge-on, as a flattened oval. From this new vantage, however, you can see the structure of the disk plainly. The arms wind clockwise from this side. There are 2 main arms, well defined, with a series of smaller arm fragments in between. Bright knots of new star formation glow along the arms in a pattern the astronomer Walter Baade, working at the Mount Wilson Observatory in California in the 1940s, once described as beads on a string. Walter Baade was the first to resolve individual stars in Andromeda's bulge, a feat made possible by an unusual circumstance during the Second World War, when blackouts in Los Angeles dimmed the sky enough for Mount Wilson to take some of the deepest photographic plates in its history. He used those plates in 1944 and the years after to discover that there are 2 distinct populations of stars in Andromeda: older, redder stars in the bulge, younger, bluer stars in the disk. That distinction, called Population 1 and Population 2, became one of the foundational ideas in stellar astronomy. Baade's work later led, in 1953, to the discovery that there were actually 2 kinds of Cepheid variables, with different intrinsic brightnesses, and that correction approximately doubled the estimated distance to Andromeda overnight. The galaxy did not move. Our understanding of where it was simply expanded. Beneath you, the disk waits. You can see the rings of star formation. There is a particularly bright one, called the 10 kiloparsec ring, which traces a circle around the center of Andromeda at a radius of roughly 32,000 light-years. This ring is brilliant in infrared light, packed with dust and young stars, and it is one of the dominant features of the galaxy's modern structure. The ring is not a permanent feature. It was likely created by the gravitational disturbance of M32, the surviving core of the swallowed giant, when M32 passed through Andromeda's disk on its way to its current orbit more than 200 million years ago. The ring is a wave. The wave is still propagating outward. The wound is still healing. Move down toward it. The dark spaces between arms become real. The arms themselves become rivers of stars. You begin to feel, in some non-physical way, that you are entering a structure rather than approaching one. The galaxy is no longer a thing in front of you. It is a place you are inside. Begin the descent into the disk. You pass through the upper layers of Andromeda's halo, where the stars are mostly old and metal poor, drifting on long elliptical orbits that take them millions of years to complete. You pass through the thick disk, where stars are slightly younger and more enriched in heavy elements, born during the great wave of star formation that the major merger triggered roughly 2 billion years ago. And then you cross into the thin disk, where the youngest stars are. Here the gas is dense. Here new stars are still being made. Here the 10 kiloparsec ring lights up around you in glowing magenta and white, full of I regions, where ultraviolet light from hot young stars is ionizing surrounding hydrogen. If you have ever stood beneath the Milky Way on a dark night and felt how the band of light arches across the sky, multiply that feeling by a factor that has no name. From inside the disk of Andromeda, the band of stars wraps completely around you, glowing in every direction. There are no constellations here. There are no patterns. There is only the gentle, relentless brightness of 1 trillion suns smeared across a sky that has no horizon. Above you, looking outward, you can see the dim halo, and beyond it, in one specific direction, away from the disk, a small flattened smudge that might, after a few seconds of recognition, resolve itself into the Milky Way. From inside Andromeda, our galaxy is the smudge. The roles have reversed. Stay with this for a moment. From inside Andromeda, looking out, our home is a faint cloud in someone else's sky. If there is a watcher anywhere in this galaxy, on any planet, around any star, they look up at the night sky and see the Milky Way as we see Andromeda, a dim oval of soft light, ancient by the time it arrives, 2.5 million years out of date. They cannot see our cities. They cannot see our televisions. They cannot, if they are looking in visible light, see anything we have made. The only photons our species has ever emitted that have reached this part of the sky are the stray radio leakage of the past 100 years, and that has only made it about 100 light years out. From the perspective of an observer in Andromeda, the human civilization on Earth has not even begun to exist. The Milky Way they see is a galaxy without us in it. Move into the spiral arm closest to you. This is the place where new stars are born. Vast molecular clouds, each tens of light years across, drift through the arm at low speeds. The arms themselves are not rigid structures rotating with the disk. They are density waves, slow-moving regions where the gas and dust pile up, compress, and trigger collapse. Stars are made in those compressed regions, then drift out the backside of the arm as the wave moves on. The arms are not roads. They are weather. The disk of Andromeda has weather, and the weather makes stars. Inside the molecular clouds, things are dark and cold. Temperatures hover near 10 Kelvin. Dust grains, each smaller than a grain of pollen, accumulate in the densest pockets and form the seed surfaces on which water ice and complex molecules can condense. In some pockets, the gravitational pull of the gathered material exceeds the outward pressure, and the cloud begins to collapse on itself. As it collapses, it spins faster and a flat disk forms. At the center of the disk, the gas heats up, ignites, and becomes a new star. Around the disk, smaller condensations may form planets. The whole process, from collapse to ignition, takes only a few 100,000 to a few million years. Fast, by cosmic standards, though slow by any human measure. This is happening now in Andromeda's arms. Right now, in this moment of your journey, somewhere in the disk you are inside, several new stars are igniting. Several more are about to. Several million planets are coalescing out of dust. Some of those planets, billions of years from now, may host their own oceans, their own continents, their own observers. Somewhere in this disk, on a world we will never see, conditions for life might be assembling for the first time. None of those observers will know about Earth. None of them will know about us. They will look up at their own pale smudge in their own night sky and think, perhaps, the same thoughts that you are thinking now, a spine checkpoint. We are now inside the disk of the Andromeda galaxy, roughly 30,000 light-years from its center. We are surrounded in every direction by 1 trillion stars and the dust between them. The Milky Way is gone from view, lost in the glow of the disk we are inside. The journey from Earth has, by any honest accounting, ended. We are standing inside the place we set out to reach. But there is more to see. We have entered Andromeda. We have not yet descended to its core. The brightest knot of the galaxy still hangs ahead of us, a glowing yellow center where the stars are densest, the dust is thickest, the gravity is strongest, and a black hole 25 to 50 times the mass of our own Sagittarius. A star sits at the very heart, waiting. And there is still the question of M32, the surviving core of the Swallow giant, orbiting nearby. There is still the question of the double nucleus. There is still the question we left at the beginning, the largest question of all. Will Andromeda meet the Milky Way? Will the trillion stars you are now flying through ever find themselves on the same orbital path as the 400 billion stars you came from? Or will the two galaxies pass each other in the dark mist, drift apart, and never quite arrive? Hold these questions. Pause for a slow breath. The arm around you glows quietly. The dust drifts in slow currents. The stars wheel in their long orbits. We are inside the place. There is more to see. The disk you are flying through has weather, and the weather is making stars, and the stars are casting their light backward through the dust and forward into a future that has not yet been written. Move further inward. You are now perhaps 20,000 light-years from Andromeda's center, riding through a region of the disk where the density of stars rises sharply and the gas grows warmer. Beneath you and above you, the disk thickens. The bright magenta of the 10 kiloparsec ring fades into yellow-white as the older stellar populations begin to dominate. The blue young giants of the outer arms give way to the red giants and the long-burning sun-like stars of the inner disk, which have lived for billions of years and will live for billions more. Recently, between 2010 and 2014, a team of astronomers using the Hubble Space Telescope carried out the largest mosaic image ever taken of any galaxy outside our own. The project was called the Panchromatic Hubble Andromeda Treasury, mercifully shortened to FAT. It captured in extraordinary detail around 117 million individual stars in a long swath stretching across roughly a third of Andromeda's disk. Each pixel in the resulting image, when you zoom in far enough, is a star, a single sun, or a small cluster of suns hanging in the dust. It is the densest, most thoroughly resolved image of an external galaxy ever produced. A successor survey called FAST has extended this work outward into the southern half of Andromeda's disk in the years that followed, with results published in 2024 and 2025. From these surveys, astronomers, for the first time, have been able to count and characterize stars across an entire spiral galaxy with the kind of precision that until then had only been possible for our own Milky Way. The portrait that emerges is intimate. Andromeda is not a smooth average. It is a place of patches. There are regions where star formation is currently strong. The ring, certain segments of the spiral arms, a few isolated knots of bright young stars near the outer disk. There are regions where star formation has all but stopped, and the existing stars are quietly aging. There are dust lanes that interrupt the light in long curves, like ink drawn through water. There are warps where the disk is bent away from a perfect plane, hints of the gravitational pulls that Andromeda has felt from past mergers and may still feel, slowly, from the orbit of M33 around it. The galaxy is not a tidy disk. It is a stained, scarred, layered, breathing place. Pause here. There is something quietly disturbing about being inside a galaxy. From outside, from the perspective of textbook diagrams, a galaxy looks like a designed object. It has arms, it has a center, it has structure. From inside, all of that resolves into stars and dust, a flowing pattern with no clear edges and no clear center, a structure so large that you cannot see it whole. We are, of course, also inside a galaxy when we stand on Earth at night. But we have lived inside it our whole lives. We have grown up under its band of light. We have learned to ignore the strangeness of our own spiral. From inside Andromeda, the strangeness is fresh. You can feel, with a kind of small chill, that you are inside an object far larger than any object you can imagine. The disk extends past the visible limit in every direction. The bulge ahead glows like a slow, distant fire. There is no shore, there is no wall, there is only the inside. Continue inward. Around you, the density of stars rises further. The ratio of dust to gas changes. The colors of the stellar population shift. Where the outer disk was streaked with the blue and pink of star-forming regions, the middle disk is increasingly washed in the warmer yellows and oranges of older suns. Some of these stars are very old. The Andromeda disk has been forming stars for at least 10 billion years, and many of its current inhabitants are several billion years older than the Sun. Some of them, in fact, are older than the Sun by margins that are difficult to absorb. There are stars in Andromeda's bulge that were already shining, already cooking heavy elements in their cores, already reaching the ends of their main sequence lives, before the protoplanetary disk that became our solar system had even begun to coalesce. When the Sun was being born, those stars were already old. A spine checkpoint. We are now 10,000 light-years from the center of Andromeda, roughly the same distance the Earth is from the center of the Milky Way, divided by 2.5. The bulge dominates the foreground. It is a yellow-white sphere of stars, slightly flattened, perhaps 15,000 light-years across, glowing with the steady, warm light of an old stellar population. From inside, you can no longer see the spiral arms. The bulge fills your field of view. The disk is now a thin layer of brightness above and below, a horizon of stars stretching out in 2 flat bands. Move into the bulge. The stars here are tightly packed. By human standards, they are still impossibly far apart, a few light months at the densest on average. But by the standards of the outer disk, where the average separation is multiple light-years, the bulge is crowded. The night sky inside the bulge, if there were planets here to look up from, would be brilliant. hundreds of stars would be brighter than the brightest stars in Earth's sky. Thousands more would crowd the visible spectrum. There would be no dark patches, no places between constellations to rest the eye. The whole sky would be one continuous gentle glow, broken by the occasional brilliant point. Stay with the strangeness of that for a moment. There are places in the universe where the sky is not dark. The classical question, why is the night sky dark when the universe is full of stars, has a long history in astronomy. It is called Olbers' paradox, after the 19th century German astronomer Heinrich Olbers, who articulated it in 1823. The resolution involves the finite age of the universe, the finite speed of light, and the expansion of space itself. But locally, the night sky is dark on Earth, because most stars are too far away to be visible. Inside Andromeda's bulge, that no longer holds. There would be enough nearby stars to fill the sky with light. A planet here, if any planet survived here long enough to evolve observers, would have a sky that never grew truly black. The whole concept of night, the basic alternation between bright day and dark night that has shaped every nervous system on Earth, would be absent. The day would simply be slightly brighter than the rest. Move further in. The bulge thickens. The light rises. The colors deepen. You are heading toward the very center of Andromeda, the place where the stellar density reaches its maximum and the gravitational pull begins to dominate the orbits of every nearby object. And now, ahead, you see it. In 1991, the Hubble Space Telescope was used to take a sharp image of Andromeda's central region. The astronomer Todd Lauer, working at the National Optical Astronomy Observatories, now part of NSF's NOI lab, analyzed the data and announced, in 1993, a discovery that had eluded ground-based telescopes for decades. The center of Andromeda was not a single point of light. It was two distinct concentrations of stars, separated by approximately 1.5 parsecs, roughly 5 light-years, sitting almost on top of each other at the very heart of the galaxy. The brighter of the two, designated P1, was offset slightly from the kinematic center. The dimmer of the two, P2, was at the true center. Buried inside P2 was a tighter, fainter cluster, later designated P3, that contained an embedded population of hot young blue stars and, at its very heart, a supermassive black hole. Andromeda has a double nucleus. That is the resolution of one of the threads we left earlier. Two bright concentrations, almost overlapping, at a single galactic center. Why? The current best explanation comes from the work of the German astronomer Ralph Bender and his colleagues, who in 2005 published a detailed kinematic study of the central region using the Hubble Space Telescope. Bender's team found that the double nucleus is not, in fact, two separate clusters of stars. It is, instead, a single eccentric ring of stars orbiting the central black hole. An oval, off-center disk, viewed at an angle, with stars piling up at the far end of their orbits, where they move more slowly. From a distance, the slow-moving end appears as the bright knot P1, and the more compact center, where the black hole sits, appears as the dimmer knot P2. The double structure is a perspective effect on a single ring. The ring has been there for a long time. It is rotating around something extraordinarily heavy at its center, and something extraordinarily heavy has a measurable mass. That mass, derived from the orbital dynamics of stars moving around the central black hole, is roughly 100 to 200 million times the mass of the Sun. There is some uncertainty in the number. Different studies, using different observational techniques, have produced different estimates. Some put it as low as 50 million solar masses. Others put it as high as 230 million. The honest answer, as always, is that we do not yet have a single agreed-upon figure. But even at the low end, Andromeda's central black hole is 25 to 50 times more massive than the central black hole of the Milky Way. It is one of the closest supermassive black holes to Earth that is significantly larger than the one in our own galaxy. And it is sitting, at this moment in your journey, only a handful of light years ahead of you, a spine checkpoint. We are now within 5 light years of the central black hole of the Andromeda galaxy. The bulge surrounds you on every side, brilliant and ancient. The young eccentric ring of stars wheels around the dark thing in the middle. We are as close as the journey can take us before the geometry begins to bend. Stop here for a moment. There is no air in this place. There is no sound. There is no familiar reference. You are surrounded by the densest stars of an alien galaxy, hanging in a sky that has no night, watching a ring of suns turn slowly around 100 million solar mass darkness, whose existence was inferred only by tracking the way those suns are moving. The black hole itself you cannot see directly. Its event horizon, the surface beyond which nothing returns, is roughly the size of our entire solar system, perhaps slightly larger, depending on which mass estimate is correct. From your current vantage, that horizon is far too small to resolve. The black hole is invisible. It is detected only by what it does to the light around it. What it does is bend the light. Stars passing close behind the event horizon, from your perspective, appear smeared and distorted. Their light is gravitationally lensed by the curvature of space-time around the black hole. Some stars on the far side appear to move impossibly fast. Some have their colors slightly shifted by the gravitational redshift as their light climbs out of the deep gravitational well. Other stars whip around the black hole on tight orbits, completing their loops in years rather than centuries. Most of them have been there for a long time. Some of them, including a population of unusually hot young blue stars near the very center, may have formed surprisingly recently in a violent burst of star formation triggered by gas falling into the central region. How exactly they formed in such a hostile environment is not fully understood. The astronomers who study this region are still arguing about it. Some think the gas was tidally compressed by the black hole's gravity. Others think the stars formed elsewhere and migrated in. The question is open. Stay with this strangeness. We are at the heart of a galaxy our species has been looking at for 1,000 years, and there are still basic questions about its center that are unsolved. We can measure the mass of its black hole to within roughly a factor of 2. We cannot fully explain how the stars closest to it got there. We cannot, despite our best instruments, see the black hole directly. We can only see what it does. The Andromeda galaxy is the easiest large galaxy in the universe to study, and we still do not understand the smallest, brightest, densest part of it. Pull back, slowly, rise out of the bulge. Let the eccentric ring of stars fall away beneath you. Let the brilliant yellow glow of the central region fade as you climb back through the disk. The disk's spiral arms reappear, glowing in their soft pink and blue. The dark dust lanes return. The 10 kiloparsec ring lights up below you in its full brightness, a glowing circle of new stars and warm dust, 200 million years old or so, since the great disturbance that triggered it. Above you, the halo opens out, stars thin, the light dims. You are leaving Andromeda the way you came in, but seeing it now from the other side of the visit, with its history of meals and mergers and disturbances written across its surface in patterns you can read. Look at it for a long moment. 1 trillion stars, a double nucleus, a black hole heavier than ours, a swallowed sibling in the form of M32, a long debris stream curling outward like the wake of an old ship, a bright ring carved into the disk by a violent passage, a young burst of stars near the very center that we cannot quite explain, a future that, as of 2025, is no longer settled. And now, the largest question of all rises, the one we left at the beginning, the one we have been carrying with us this entire journey. Will Andromeda meet the Milky Way? The honest answer, as we now know, is that we do not know. For nearly a century, since the careful proper motion measurements of the early 20th century, the consensus was that the merger was inevitable. By 2012, when Roland van der Marel and Tony Sohn at the Space Telescope Science Institute in Baltimore, Maryland, published their detailed Hubble analysis, the merger seemed all but certain. A head-on collision in roughly 4 to 5 billion years, leading to the formation of a new elliptical galaxy that some commentators began calling Milkomeda. The textbooks were rewritten to reflect that prediction. Documentaries were produced. Computer simulations of the night sky in 3 to 4 billion years became staples of popular astronomy. The story was clean. The story was settled. The story was wrong. Or at least, the story was no longer all there was. In 2025, when Sawala's team at Helsinki ran their 100,000 simulations with all 22 variables, with the latest data from Hubble and Gaia, with the gravitational influence of M33 and the Large Magellanic Cloud taken into account, the merger probability dropped to approximately 50% over the next 10 billion years. Half the time, the two galaxies meet. Half the time, they pass each other in the dark, separated by perhaps 500,000 light-years on closest approach, then drift apart, then perhaps fall back together over much longer timescales. Perhaps not. The Magellanic Cloud's mass, as it orbits the Milky Way, pulls our galaxy off the orbital plane that would lead to a head-on encounter. M33's mass, orbiting Andromeda, pulls in the opposite direction. The two influences nearly cancel. What is left is a coin flip. How can this be? How can a question that seemed settled become unsettled? How can a decade of new data make the answer less certain rather than more? How can a galaxy, drifting toward us at a measurable speed, fail to arrive? The answers are not satisfying in the way clean stories are satisfying. They are honest. The reason the merger probability fell from near certainty to 50-50 is that, with better data, astronomers were able to take more variables seriously. The 2012 calculation used a simplified model in which the Milky Way and Andromeda were treated as isolated objects. The 2025 calculation took into account the full system, including M33, the Large Magellanic Cloud, and the gravitational influence of dark matter halos around all of them. With more variables came more uncertainty. The underlying physics did not change. The galaxies are still there. The motions are still measured. The masses are still estimated. But the future is more sensitively dependent on those measurements than the simple model suggested. A small uncertainty in Andromeda's sideways velocity, multiplied by 10 billion years, becomes a vast uncertainty in where Andromeda ends up. A small uncertainty in the Magellanic Cloud's mass, integrated over the same time frame, becomes a vast difference in what the Milky Way's orbit looks like. The numbers have not gotten worse. Honesty has gotten better. And here is the question that follows, the one that turns this whole journey on its axis. What does it mean that we cannot know? What does it mean that one of the most famous predictions in modern astronomy, the predicted death of our night sky in fire, is now genuinely uncertain. What does it mean that we live in a century where the future of our galaxy has become, again, an open question? What does it mean that for 30 years popular science told us with confidence that the sky would burn, and that we now have to admit in the same calm voice that it might not? Stay with these questions. Do not rush to the answer. There is a paradigm shift hidden inside them. The old picture, the one we grew up with, Andromeda inevitable, merger certain, the future of the night sky, a single fixed cinematic fate, was a story shaped to be told. It had a beginning, a middle, an end. It had a character, Andromeda, with a destination, us. It had stakes, the destruction of our familiar sky. It was, in the structural sense, a narrative. But galaxies do not have narratives. Galaxies have probabilities. The Andromeda galaxy is not on a journey. It is in an orbit whose details depend on the mass of every nearby object, including objects we are still discovering. The future of the local group is not a story. It is a probability distribution, with uncertainties on every variable, and the most honest version of the prediction is not a single line on a graph, but a fan of possibilities widening into the deep future. We have been telling ourselves stories about the cosmos for as long as we have been able to tell stories. We have given galaxies fates. We have given comets visitations. We have given stars destinies. The cosmos, we now have to admit, does not always cooperate with the structure of narrative. Sometimes the answer is 50%. Sometimes the answer is, we cannot know yet. Sometimes the only honest report a scientist can file is a probability, not a story. How does this change what we have done tonight? You traveled across 2.5 million light years to visit a galaxy. You crossed the solar system, the Milky Way, the void between, the halo, the disk, the bulge, the nucleus. You witnessed the eccentric ring around the central black hole. You looked back at the Milky Way as a smudge in someone else's sky. You absorbed the strangeness of star formation, the weight of old stars, the scars of past mergers, the silence of intergalactic space. And at the end of all that, you are forced to admit that even with everything we have learned, even with the largest space telescopes in human history, even with the world's best Monte Carlo simulations running on the world's best computers, we do not know whether the galaxy you just visited and the galaxy you came from will ever actually meet. That is the kind of truth science gives you. It is honest. It is unsatisfying in the way honest things often are. It does not resolve. It admits its limit. The Sawala team, in their paper, used a phrase that captures this directly. Proclamations of the impending demise of our galaxy seem greatly exaggerated. They did not say the demise is impossible. They said it is no longer certain. The cosmos, having been told it had a destiny, has politely declined to confirm it. There is something liberating in this, and something quietly heavy. The liberating part is that the future of the night sky is not a fixed sentence. It is open. The Milky Way may continue undisturbed for another 20 or 30 billion years, swinging through the empty regions of intergalactic space, while Andromeda passes us by like a stranger on a long road. Or we may meet. Or we may meet later than expected, after a long, careful waltz of orbital approach and retreat. The story has more endings than the textbooks said it had. The heavy part is that even as we have built telescopes that can see across 2.5 million light years, we are still not powerful enough to predict, with confidence, what happens to our own back garden in the deep future. The honest position on the largest question we know how to ask is uncertainty. What if, then, the journey we just took was not a journey to a place, but to a question? What if Andromeda is not a destination, but a mirror? What if every galaxy we have ever charted, every collision we have ever simulated, every fate we have ever pinned to the future, is at some level a story we are telling ourselves about a universe that does not need stories? What if the most important thing the Andromeda galaxy is doing, right now, is showing us that we are not yet powerful enough to know our own future? Hold these questions. There is no answer. There is, in this part of the journey, only the asking. Stand on a hilltop on a clear autumn night, far from city lights, far from any window with a lamp. Let the cold settle on your face. Let your breath pale in front of you. Tilt your head back until the stars take up the whole of your vision, until the rim of the horizon is below your awareness, and there is only the deep dark above, sprinkled with light. Find the constellation Cassiopeia, the lazy W of bright stars high in the northern sky. Drop your gaze a little to the south. Find the line of stars that traces the constellation Andromeda. Aim for the second brightest star in that line. Then, just to one side of it, slightly above and to the right depending on the season, look for the smudge. It is small. It is faint. It is paler than the stars around it, more diffuse, with no sharp edge. If you have never noticed it before, your first sight of it may be disappointing. The textbooks make it look so dramatic. The smudge in person is humble. It is the kind of thing you have to know is there in order to see. Once you see it, you cannot unsee it. It hangs there, every clear night in the same place, never moving on the human timescale, never twinkling, never blinking. That is the place we just visited. That is the place whose disk we descended into, whose bulge we crossed, whose central black hole we approached as closely as the geometry permitted. The smudge above your hilltop is the same object. The light reaching your eyes left it 2.5 million years ago, traveled across the void we crossed, fell through the halo of the Milky Way, dropped down through the disk, threaded between the stars of our local stellar neighborhood, passed by the solar system, slipped into Earth's atmosphere, and arrived on your retina as a faint, pale glow. You and the smudge are connected by photons. You and the smudge are connected, more than that, by the fact that you have now imagined yourself standing inside it. You have done a thing the photons cannot do. You have made the trip in both directions. Stay on the hilltop. Let the chill of the night air remain on your skin. Let your shoulders drop. Let your breathing slow. Notice, around the smudge, the other faint patches of light that fill the dark sky. Not the bright, sharp stars, but the diffuse glows that astronomers spent their careers cataloguing. There are other galaxies up there. The Triangulum Galaxy, M33, the third largest member of our local group, hangs not far from Andromeda. It is dimmer, smaller, farther, but it is up there. There are dwarf galaxies you cannot see without binoculars, and you cannot see most of them at all without a telescope. There is, in every direction, a quiet ocean of other galaxies, most of them too far away to be visible with the naked eye, but present. Picture yourself then, on this hilltop, on this planet, in this small corner of one ordinary spiral, surrounded by a sky that contains uncountable other spirals just like it. Picture, gently, the other planets that may exist in those other spirals. Picture the other observers on those other planets, on their own hilltops looking back. The light of the Milky Way is reaching them too, somewhere out there, in the same patient way that Andromeda's light is reaching you. They cannot see your hilltop. You cannot see theirs. But the photons are exchanging. There is a kind of communication in this, even though no message is being sent. You and a possible observer in Andromeda are exchanging information about the existence of your galaxies. The light from Andromeda is reaching you with structure, with color, with hints of star formation and dust and an ancient violent merger 2 billion years gone. The light from the Milky Way is reaching them with structure, with color, with hints of our own history. Neither of you can answer the other. Neither of you can write back. The conversation is one-directional and infinitely slow. But it is a conversation in the only sense the universe seems to permit between things separated by such distances. We send light. Light arrives. The arrival is the message. Sit with that for a long, slow moment. The smudge above you is a letter. The hilltop you are standing on is a mailbox. The conversation is older than language, older than fire, older than the first human face. The conversation will continue long after every face is gone. The cold deepens around you. The constellations move slightly through the night, swinging westward. The smudge stays where it is, anchored in its piece of the sky. It does not appear to move on a human timescale. To the casual observer, the night sky is fixed. To the astronomer with patient instruments, the smudge is drifting toward us at 110 kilometers per second. But the drift is so slow against the distance that it produces no visible effect within a single human lifetime, or even within the entire span of human civilization. The smudge, to all our senses, sits still. It has sat still in our sky for as long as we have had eyes to see it. It will sit there, in roughly its current position, for another few 100 million years before any naked eye observer would notice that it had moved appreciably closer. Stay with the slowness. There is a particular kind of comfort in cosmic slowness, even when its endpoints are dramatic. Whatever is going to happen between Andromeda and the Milky Way, whether they meet, whether they miss, whether they swing past and return, none of it is going to happen quickly. None of it is going to happen on the timescale of any worry you have ever had. None of it is going to happen on the timescale of any country, any language, any civilization, any species. The drama of cosmic gravity moves at the pace of cosmic gravity. The smudge above your head is, for all human purposes, eternal. There is also a kind of weight in this. The slowness is comforting only until you remember that all of the things you care about, your own life, the lives of everyone you love, the future of your culture, the fate of your planet, happen on timescales so much shorter than the ones we have just been describing that they nearly disappear into the dust of the calendar. The sun will run out of hydrogen in roughly 5 billion years. The Earth, by then, will likely be uninhabitable, swallowed or scorched by the dying star. Whether the Milky Way merges with Andromeda or not is a question that, for any creature recognizable as human, has no consequence. Even if the merger happens, it happens long after our planet has ended. We are not the audience for the cosmic show. We are the warm-up act. This is the quiet truth of the smudge. It is not coming for us. It will not arrive in time. Whatever happens to it will happen to whoever, if anyone, is left to watch. The story we have been told about Andromeda swallowing the Milky Way and igniting the night sky and fire is, even at its most certain, a story about a future we will not be present in. The cinematic image of two galaxies tangling above a darkened Earth assumes the survival of an Earth that, by then, will not exist in any habitable form. Stand quietly on the hilltop. Let the smudge stay where it is. Let your body settle. The journey is, in one sense, complete. You have visited the place. You have come home. The night air is cold. The grass is damp. The stars wheel slowly. Above you, the smudge holds its place. There is one last layer to feel. We turn to it now. Imagine, instead of standing alone on the hilltop, You are standing on the slope where some unknown ancestor stood 1200 years ago, somewhere in the mountains of Persia, at the height of a great civilization of scholars and cartographers and astronomers. You are not al-Rahman al-Sufi himself. You are someone earlier or later or beside him. You are any one of the thousands of human beings throughout the ages who have stood under a clear night sky, looked up, and noticed the faint cloud in the constellation we now call Andromeda. You did not know it was a galaxy. You did not know what a galaxy was. You did not know that the cloud you were seeing was made of 1 trillion stars, that its light was older than your species, that the photons reaching your eye had begun their journey before any human being had learned to make a fire. You only knew that there was a smear of pale light in a particular part of the sky, on a particular kind of clear, cold night, and that it was strange and quiet and beautiful. You watched it. Perhaps you described it to a child. Perhaps you wrote it down. 1200 years passed between al-Sufi's careful recording in 964 and Edwin Hubble's photographic plate in 1924 that finally proved the smudge was a galaxy. 12 centuries, 40 generations. An empire of telescopes had to be built before the cloud al-Sufi described became something we could measure. And then, only a century later, we were able to map its disk, count its stars, weigh its black hole, simulate its trajectory, and finally, with all the precision the 21st century could give us, admit that we could not predict its future. The smudge began as a question for al-Sufi, was recorded as a question, was inherited as a question, was answered partway by Hubble, was answered further by Bard, was answered still further by van der Marel and Zohn, and then was returned in 2025 to a kind of question again. The cloud has been a question for more than 1,000 years. There is a kind of cathedral being built here, not a stone one, a scientific one. The image of medieval cathedral construction in Europe is the relevant historical parallel. In the 12th and 13th centuries, in places like Chartres and Cologne and Reims, masons began work on cathedrals so large and so intricate that no one alive at the laying of the cornerstone could possibly hope to see the building completed. The cathedral at Cologne, in Germany, was begun in 1248 and not formally completed until 1880, 632 years later. The masons who carved the first arches did not see the spires. The architects who drew the first plans did not live to see the floor finished. They worked instead with a clear understanding that the cathedral was not a project for any single human life. It was a project for a culture across centuries, with each generation contributing whatever stone they could place during their short turn and trusting that other generations before and after would do the same. The result was an object that no individual could have built and that no individual could fully see, but that every contributor became part of through the act of placing their piece. The map of Andromeda is a cathedral of this kind. Al-Sufi laid the first stone in 964 by writing the description down. Galileo, with his small telescope in early 17th century Italy, refined the view. Charles Messier, in 18th century France, gave it a number. William Herschel, in late 18th century England, charted its shape. Vesto Slipher, at Lowell Observatory in Arizona in 1912, measured its motion. Edwin Hubble, on Mount Wilson in California in 1924, established its distance. Walter Baade, on the same mountain in the 1940s and 1950s, sorted out its stellar populations. Ralph Bender, in 2005, made sense of its strange double nucleus. Rodrigo Ibata and Annette Ferguson, in 2001, found the long debris stream that revealed its Eton sibling. Richard D'Souza and Eric Bell in 2018 identified the swallowed galaxy as M32's progenitor. Roland van der Marel and Tony Sohn in 2012 measured its sideways drift through the sky. Til Sawala and his international team in 2025 ran 100,000 simulations to test whether the merger we had predicted for over a decade was actually inevitable. None of them did the work alone. None of them saw the building complete. None of them, even now, can stand in a finished hall and admire the whole thing. The Cathedral of Andromeda is still being built. The next stones will be placed by astronomers not yet born, with telescopes not yet imagined, working from data not yet gathered. We will not see the building completed. We are partway up the wall. There is something quietly noble about this. The cathedral metaphor is accurate, not just in its scale, but in its character. The masons who placed the first stones at Cologne did not work for personal glory. They did not expect to see their names attached to the finished building. They knew that what they were making was a structure for a community, across time, in service of something larger than any one of them. The astronomers who chart Andromeda are working in the same mode. They are not building a monument to themselves. They are placing stones in a long, ongoing project to understand the universe, knowing at every step that the picture will be revised, that the next generation will have better tools, that the answers they confidently report this year may be questioned the next, that the merger they are sure of in 2012 may become a 50-50 coin flip in 2025. The work continues regardless. The stones keep getting placed. This is finally what the Andromeda galaxy means for us. Not its mass, not its distance, not its trajectory, not even its possible meeting with our own galaxy. What it means is that, for 1,000 years, we have been pointing instruments at one particular smudge in our sky, and slowly, patiently, generation by generation, building a more accurate picture of what is out there. Each generation has handed the work to the next, with humility, with corrections, with new uncertainties revealed. Each generation has stood under the same smudge and asked the same fundamental question in different terms, with different precision. What is that thing? What is it doing? What will become of it? What, if anything, will become of us with respect to it? We have not arrived at the final answer. We may never arrive at the final answer. The merger may happen in 5 billion years, or 10, or never, and even our best simulations now admit that they cannot tell us which. But the question is what we have been asking, all this time, all of us together. The medieval astronomer in Persia, the Italian with the spyglass, the photographer on the California mountaintop, the Finnish team running their simulations. We have all, in our various ways, looked at the smudge and asked. We are still asking. The asking is the cathedral. The asking is what we are building. Stand on the hilltop. Look at the smudge. Recognize now that the cloud above you is not just a galaxy. It is a 1,000-year conversation among human minds. It is proof that a species which lives only a few decades can still construct across many generations an understanding of objects that span millions of light years. It is the form our species has chosen to take when faced with the cosmic. We do not stop asking. We do not give up. We do not pretend to know more than we do. We pass the question on. That is what Andromeda has been for us all along. A 2.5 million light-year distant question written into our sky that we have been working on since the first careful eyes paid attention. The work continues. The merger is uncertain. The night above your head is dark. The smudge waits. There is one final perspective. Imagine gently the planet beneath your feet. 5 billion years from now, in the version of the future where the merger does occur. The Sun, by then, will have left the main sequence. Earth will be gone, or scorched, or swallowed. Whatever life remains in the solar system will not be in any form we would recognize. The night sky over what was once Earth, if there is any night sky still being observed, will not be the sky we know. Andromeda will hang in it, much larger than it does now, perhaps as wide as the Moon. The two galaxies will be approaching each other, their tidal forces beginning to deform their disks, the first long arms of stars being flung out into the space between them. There will be no humans to watch this. There will be no human telescopes. There will be only the slow gravitational ballet of 2 trillion stars, drifting through each other on a timescale that has nothing to do with us. Imagine, then, the version of the future where the merger does not occur. In that branch of possibility, the two galaxies pass each other in the dark, separated by 500,000 light-years on closest approach. The night sky over the long-dead Earth, again with no observers, sees Andromeda swell and then recede, growing brighter for a few 100 million years, then dimming again as the larger galaxy moves on into deeper space. The two great spirals continue in their long orbital dance, perhaps to meet much later, perhaps not. The local group reorganizes around their passage. Eventually, in this branch, the universe's accelerating expansion carries our two galaxies apart faster than gravity can pull them together, and the merger that once seemed inevitable simply never happens. The night sky over the cold remnant of our planet remains, for whoever or whatever might be looking, a quiet field of slowly receding lights. These two futures hang in the same sky above your hilltop tonight. Both of them are possible. Both of them are in some real sense already determined by the physics of the present moment. But neither of them is determined enough that we, with all our instruments, can yet tell which one we are in. The smudge above you contains both. The light reaching your eye is consistent with both. The future of our galaxy and our descendants, if any descendants are imaginable, branches above your head to possibilities that science can only describe as probabilities. This is what it is to live in a universe with honest uncertainty. The cosmos does not always tell you which version is going to happen. Sometimes it tells you the odds. Sometimes the odds are 50-50, and the only response a careful person can offer is to keep the question open, to keep building the cathedral, to keep placing stones, and to trust that the generations after us will see further than we have, and admit, as we now admit, that they too will not see the whole thing. Hold this above you. Hold the smudge. Hold both futures. The night air is cold. The hilltop is real. The stars wheel slowly westward. The conversation continues. This is what we have done tonight. We began on the surface of an ordinary planet, around an ordinary star, in an ordinary spiral. And we found, in the autumn sky above our heads, a small pale smudge that was older and larger than anything our species has ever built. We learned that the smudge had a name in the year 964, when al-Rahman al-Sufi wrote it down in the Book of Fixed Stars, not knowing what he had seen. We learned that the smudge was confirmed as another galaxy in 1924, when Edwin Hubble, on Mount Wilson in California, used Cepheid variables to measure how far away it was. We learned that the smudge is approximately 2.5 million light-years from us, that its diameter is roughly 200,000 light-years, that it contains around 1 trillion stars, and that its central black hole is between 100 and 200 million times the mass of the Sun. We learned that it is approaching us at 110 kilometers per second, and that this approach, until 2025, was widely believed to result in a head-on collision in roughly 4 to 5 billion years. We learned then that this picture has been quietly rewritten, till Sawala's team, working from the University of Helsinki in Finland with collaborators across Europe and Australia, ran 100,000 simulations of the local group's evolution, taking into account the masses and motions of the Milky Way, Andromeda, M33, and the Large Magellanic Cloud. They found that the merger probability over the next 10 billion years is approximately 50%. The most famous prediction in modern astronomy has become, again, a coin flip. We did not stop with the numbers. We left the surface of our planet and traveled, as nobody can, across the geography of the cosmos. We crossed the solar system and watched the sun shrink to a single point of light. We crossed the disk of the Milky Way, threaded through nurseries of new stars, drifted past the dust lanes and the molecular clouds and the supermassive black hole at our own galactic center. We climbed up out of the halo and crossed the void between galaxies, where the air is so thin it is more vacuum than substance, where the cosmic microwave background hums in every direction, at a temperature only a few degrees above absolute zero. We approached Andromeda from the outside and saw its halo of ancient stars, its scattered globular clusters, the long curving arc of the giant stream, the wake of a galaxy Andromeda swallowed 2 billion years ago, whose surviving heart still drifts beside it as the small dense companion called M32. We descended into the disk. We passed through the bright 10 kiloparsec ring, where new stars are being born in the wake of an old disturbance. We entered the bulge, where the sky never grows dark and the stars are old and crowded. We approached the heart of the galaxy and found a strange double brightness, the eccentric ring of stars discovered by Todd Lauer in 1993, and explained in the years that followed by Ralph Bender's careful kinematic study as a single off-center disk wheeling around a hidden supermassive black hole. We stood as close to that black hole as the geometry permitted and recognized that we could not see it directly. We could only see what it does to the light around it. And then we pulled back. We left Andromeda the way we came in. We crossed the void in reverse. We returned to the disk of the Milky Way, returned to the local stellar neighborhood, returned to our solar system, returned to our planet, returned to our hilltop. We came home. But the home we returned to is not quite the home we left. The smudge above the autumn horizon is no longer just a smudge. It is a place we have been. It is a galaxy whose internal weather we have witnessed, whose history of violence we have read in its scars, whose central darkness we have approached, whose future we have been forced to admit we cannot yet predict. It is a 1,000-year conversation among human minds, beginning with al-Sufi in medieval Persia and continuing tonight with you on a hilltop or in a quiet room, listening to a story about something that has been visible to every careful eye for the entire history of our species. It is a cathedral still being built. We have placed our stones. The next generations will place theirs. What does it mean that we cannot know? What does it mean that the most famous galactic prediction of the past century has been quietly returned to a question? It means, as honestly as we can say it, that the universe is not always cooperative with the structure of narrative. The cosmos has probabilities, not destinies. The Andromeda galaxy is not on a journey to meet us. It is in an orbit. The orbit has uncertainties. The uncertainties widen with time. The future, even the parts of the future that physics is supposed to predict cleanly, has more openness in it than the textbook diagrams admitted. We have learned that admitting this is not a failure. It is a form of intellectual maturity. The honest report, after 1,000 years of looking, is that the smudge will do what the smudge will do, and we will not know which thing it does until we have measured for considerably longer than we have measured so far. There is melancholy in this, and there is also a quiet kind of awe. The melancholy comes from recognizing that no human being will ever stand on a real hilltop and watch Andromeda arrive, or fail to arrive. None of us will live that long. None of our descendants, in any form recognizable as ours, will live that long either. The sun will end before the question resolves. The earth will end before the question resolves. The story we have been telling ourselves about a fiery merger of galaxies above the heads of distant future humans is, at its most honest, a story about a future we will not be present in. The smudge above the hilltop will outlive us. The question of its meeting with our own galaxy will outlive every species, every culture, every memory we have ever made. The awe comes from the same fact, seen from a different angle. We have built, in the time our species has had, an understanding of an object 2.5 million light-years away that is detailed enough to argue, intelligently, about its future trajectory across the next 10 billion years. We have measured its mass to within roughly a factor of 2. We have charted its arms, named its rings, weighed its black hole, identified its swallowed sibling, traced the wake of its old meal across the halo. We have simulated its possible futures 100,000 times. We have done all of this on a planet that is itself only 4.5 billion years old, with a science that is barely 400 years old, with telescopes that are barely a century old, by adding stones, generation after generation, to a building none of us will ever see complete. That is what our species has done with its time. That, more than any single discovery, is the thing worth standing quietly on a hilltop on a clear autumn night. Look at the smudge again. Notice it is still where it was. Notice it has not moved. Notice that, despite all the journeying we just did, all the descents and ascents, all the orbits and stars and dust lanes and black holes, the actual cloud above your head is exactly as it was at the start, 2.5 million light-years away, drifting toward us at 110 kilometers per second, carrying 1 trillion stars and a black hole heavier than ours and an old wound from a galaxy it ate 2 billion years ago. Photons leaving its surface now will not reach Earth, or whatever is here in place of Earth, for another 2.5 million years. The smudge has been patient with our species. It will continue to be patient long after our species ends. It is, in the way only cosmic objects can be, indifferent. It is also, in the way only cosmic objects can be, beautiful. Stand with that. The cold air on your face, the grass beneath your feet, the slow sweep of the constellations westward, the smudge holding its place. Above you, 2 futures still hang in the same patch of sky. In one, our galaxy and its neighbor will meet, sometime in the deep future, and merge into a single new structure that humans, if any humans were left to name it, might call Milkomeda. In the other, our galaxy and its neighbor will pass each other in the dark, miss, drift onward, and never come together at all. Both versions are written into the same smudge. Both versions are consistent with the same light reaching your eyes tonight. The cosmos has not yet told us which one we are in. The cosmos perhaps will not tell us at all, and the question will simply continue to be passed forward, generation by generation, until the species capable of asking it is gone. That is the journey we have taken, from a planet to a smudge, from a smudge to a galaxy, from a galaxy back to a planet, with 1,000 years of human astronomy carried alongside us the whole way. If this changed how you think about the clouds in the autumn sky, then the time was well spent. If you find yourself on the next clear night, looking for the smudge in the constellation Andromeda, and remembering, even faintly, that you have stood inside it, that the photons reaching your eye have crossed a distance you have now traveled in your imagination, then the work of the cathedral has been continued in some small private way in you. Thank you for staying. Thank you for letting your shoulders drop, for slowing your breath, for crossing the void with patience. The smudge is still there. It will be there tomorrow and the night after that, and for as long as anyone is left to look. Hold the cold air for one last moment. Tilt your head back. Find the lazy W of Cassiopeia. Drop your gaze a little to the south. Find the line of stars that traces Andromeda. Aim for the second brightest star in that line. Then, just to one side of it, slightly above and to the right, look for the smudge. There it is, 2.5 million light years away, drifting, beautiful, patient, ours in the only sense that anything cosmic can be ours. The conversation continues. The cathedral grows. The night holds. Sleep well.